Okay, welcome back to the 3.2 notes. And what we're going to do right now is we're going to look at how to graph derivatives. And so what we do is we look at the graph of our function f to sketch a graph of f prime of x. Okay, so on this first one, I want to start off kind of basic and show you how we graph this. The first thing that I want to show you guys is that this line, at any point along this graph, I'm asking myself the question, what is the slope at any point along this graph, okay, if I have a line? And the slope, up 2 over 1, this has a slope of m equals 2, okay? So at any point where I have this graph of a slope of 2, my derivative is going to be 2. So I plot the value of 2. Now here's the problem, okay? What's happening at 1? 1, this is a corner, okay? This is not differentiable here because we switched derivatives. All right, now the other thing I want to do here is say, okay, well, what's the slope of this line? Okay, the slope of this line is -1. So what I do is I go down here to -1, and I plot that graph at -1, okay? So this is what it means. And so on this function would be f prime of x. Okay, let me ask the question, what's f prime of 1? Nothing. It's undefined. Okay, that's what it means to be differentiable. Okay, um, kind of putting this into a little perspective here of what this looks like. So that's what it is. Okay, that's what a derivative is. Remember, a derivative is a function. Okay, so I look at the slope, and then my slope becomes the y value. So the slope, let me write this, the slope at a point at an x value becomes the y value of my derivative. Okay. Okay, so it's pretty easy to do this when you have a linear function, but let's take a look at something that's nonlinear. Okay, let's look at a parabola. And the first thing that I want to do, you're given this function here, f of x is equal to x squared. If we were to do the limit definition of a derivative and calculate this derivative, then the derivative here that we'll get is f prime of x is equal to 2x, okay? So that's the first thing I want you to write. If you want to do the limit definition of the derivative to find that, you can. That's what you get. I just don't have time to do that in the video right now. Okay, but what I want to do is I want to graph this function 2x, okay? We'll do that here in a second, but I want to look at each point along this parabola, and I want to determine what the slope is at each one of these points. And basically what I want to do is I'm going to come here, and at each one of these points, let me hopefully do a better job of this, I want to graph the tangent lines at each one of these points, okay? And as I move from left to right, my slopes are negative. They're all negative, but they're getting less and less and less steep until they get to this point down here, which is a 0, okay? This slope down here is 0. Coincidentally, I have a minimum, okay? And then all of a sudden it changes, and the slopes of my tangent lines become positive. So here's the thing that we need to realize, guys, is that what I'm trying to do here is as I'm seeing that these slopes change from negative slopes, they get less and less and less negative till they get to 0, and then they get more and more positive, okay? So what I want to do is, let's do this real quick. Let's actually make a table for x and then f prime of x, okay? So, and I want to look at the x values of -2, I want to look at -1, I want to look at 0, I want to look at 1, and then I want to look also at 2, okay? And what I'm going to do is remember, the derivative is something that generates a slope of the tangent line, okay? So what I want to do is I want to look at -2, okay? At this point right here, what is the slope of this tangent line at -2? Well, if I plug in -2 into this function, I get a slope of -4. Okay, this is the slope at x equals 2, or I'm sorry, -2. Okay, let's take a look at -1. At this point, what's this slope? This slope appears to be, it looks like it's about -2. Okay, and if I plug it into my derivative function, I get 2 times -1 gives me -2. Again, this is the slope, okay, at x equals -1. Okay, if I plug in 0 into my derivative, I get a slope of 0. Okay, and this is the slope at x equals 0. Okay, if I plug in 1, all right, what's the slope of the tangent line at 1 at this point? And if I plug that into my derivative, I'm going to get 2. Okay, and that's the slope, okay, at x equals 1. All right, now if I plug in 2 here, I have a point 24. But if I plug that in, then I get the point 4. Okay, I get a slope of 4. I'm sorry. So I get a slope. That's 4 is my slope at x is equal to 2. So here's the deal. My slope changes. Okay, as x changes, so does the values of my slope. Now, what hopefully you see here, guys, is that these create a function. I can actually plot these points. And if I plot these points, and bear with me on this, okay, but if I plot these points, then I get -2, 4, that's all the way down here. I'm going to do -1, -2, I'm going to plot that point. 0, 0, if I plot that point, it's right here. If I plot the point 1, 2, I get this point, and then I have the point 2, 4. Okay, and if I connect these with a line, I don't want to use that. This one from the other one. Let's use the black one. If I connect these with a line, okay, I get another function. Okay, and I get a derivative function. Okay, and I can graph that, and these are related. Okay, and the one thing I really want you to see is that look where my graph crosses the x-axis. It crosses it at 0. That's also where I have a minimum. Okay, so that's something important. So what I notice here is that the slopes here are negative. They're getting less and less negative. Okay, then I plot negative values on my derivative. When I have a minimum, my slope of the tangent line is 0. So I plot 0, and then these values get more, the slopes get more and more steep, more and more positive. So as x gets bigger, my slope gets steeper, and my y values of my derivative get larger. Okay, so that's how I'm doing this. All right, so these two graphs, even though they're different, they are directly related to each other. Okay, so let's take a look at another one. Let's look at this graph. F of x is equal to x cubed, and do the exact same thing. What I want to do here is I want to show you that my derivative, f prime of x, if I were to use the limit definition of a derivative, I would get the derivative 3x squared. Okay, I don't want to go through that because I don't have the time to. But let's go ahead and let's look at all these different values here. Okay, if I were to find the slopes of all of these different little tangent lines, what I notice is that my slopes, when x is negative over here, these slopes are positive. Okay, and then they get less and less positive, they get less and less steep, they kind of approach 0. Okay, and right here I have a horizontal tangent of 0, and then all of a sudden these slopes get more and more positive again. Okay, so nothing too crazy, but let's think about the shape that I get. Okay, and I'm going to get a parabola. Okay, so let's take a look. Let's actually draw these points out. Let's do, I don't want to do that. Let me do x values and y values, or I'm sorry, f prime of x values. And so let me do just -1, 0, and 1. Okay, and if I plug these values into my derivative, I'm going to get +3 out of this. Okay, if I take the value of 0, okay, I have a slope of the tangent line at 0. So hold on, let me do this. At -1 here, at this, the slope of this line, okay, it looks like it's about +3. Okay, if you were to extend this line out, it looks like it has a slope of about 3. Okay, the slope here at 0 is a horizontal slope of 0. Okay, if I plug in 1 here, into my derivative, my slope looks like it's about 3, okay? So if I plug 1 into my derivative, I get 1 squared times 3. That's just 3, okay? So let's think about this for a second. If I plot this value of my derivative here at 3, okay, I get that point there. I have the point 0, 0, and then I have the point 1, 3, okay? And so if I draw that, all right, I'm going to get a parabola that opens up, okay? And it would continue on, okay? I bet if I plugged in -2, found the slope of the tangent line at -2, I bet it would be, what is that? If it was -2, what would we get? -2 squared, we get, what do we get? 12, okay? And if I did +2, we would also get 12, okay? So those points aren't on the graph, but that's the idea, okay? So I'm using these little tangent lines to help me graph where these go, okay? So let's take a look. Let's do this one real quick, the square root of x. And all I'm going to do is just kind of look at the slopes and graph this. Those other ones I can do pretty easily. This one's a little bit harder. Now this one's interesting because my domain is restricted on my function, okay? I'm going to take all these little tangent lines. Now right here at 0, I have a vertical tangent, okay? And this is, square root of x is just a sideways parabola, okay? So then what I'm going to do is I need to look at what happens to my slopes. They're really, really, really steep. And then as x gets bigger, the values of my slopes get less and less steep. So the value of my slopes goes down. Okay, so I have all these different slopes. They're getting less and less steep as x gets bigger. All right, and so if I were to plot those points, okay, I would, because it's undefined, I actually have an asymptote here. But I end up getting something like this. I end up getting these values that they're really, really, really steep, and then they start to level out, and then they start to gradually go that way. Okay, so this is a graph, here in red, this is the graph of my f of x, okay? And then the blue one, this is a graph of my derivative, f prime of x. So a good idea, and I already know that the derivative of f prime of x is equal to 1 over 2 times the square root of x. And if you were to graph this, this is what it's going to look like, okay? We will do this one in class, so don't worry about that one too much. We'll do that one as like a bell work problem or something. But let's go ahead and take a look at these problems here, okay? And this is kind of asking questions about differentiability and continuity. And the question is, all right, my domain goes from -2 to 3, okay? So these are endpoints on this graph. And there's something to talk about with endpoints and differentiability. The question is what's the derivative of this function at -2, okay? And the way you have to think about it is that in order for a derivative to exist, we have to have a two-sided limit. But we can think of one-sided derivatives here. This is pretty particular, but it just depends on when do we talk about functions that are, where are they differentiable? Do I have a derivative at -2? Some books will say that you do have a derivative at -2. Some books will say that you don't have a derivative at -2. Here's what I know. Okay, the graph is continuous. Okay, let's look at where is the graph continuous. Okay, and let's just look about continuity. Okay, my graph is continuous between -2, include -2, to 0. Okay, union that with from 0 to 2. Okay, and then union that from 2 to 3. But we include 3. That's where it's continuous. When we're talking about differentiability, we're talking about the values in between these values. Okay, we're not specifically always talking about the endpoints, but I want to kind of make it clear that just because it's continuous doesn't mean it's always differentiable, but you can consider these endpoints to be differentiable, but maybe not. Okay, so let's take a look. Where are we differentiable? We're differentiable everywhere. Well, we're not differentiable at -1. Okay, so we're differentiable. I'm going to do -2 to 1, -1, union that with from -1 to 0. Okay, union that from 0 to 2. Okay, and then union that from 2 to 3. Okay, and I'm going to go ahead and just include the endpoints. I'm not going to count off if you don't. That's okay. Okay, so the question is, where are we continuous but not differentiable? Okay, so look at our continuity. Continuity, we included 1 or -1. Okay, so that would be at x equals -1. That's where we're continuous, but we're not differentiable there. Okay, the question is, where are we neither continuous nor differentiable? That would be at x equals 1, I'm sorry, -1. Wait, no, that is where it's continuous. Where are we not continuous? Okay, and so if we're not continuous, we're not differentiable. So that would be at x equals 0 and x is equal to 2. Okay, that's where we're not continuous. All right. All right, let's take a look at the last one. The last one shows we're recovering a function from its derivative. And you know what, guys? I'm going to go ahead and stop the video there. We're at 15 minutes. We'll do that one in class. So I hope this made sense to you. Please get started on your homework, and we'll see you soon. Thanks. Bye.